Picture a world where gleaming white turbines stretch as far as the eye can see, their massive blades slicing through the air with hypnotic precision. These sentinels of clean energy stand tall against the horizon, promising a future free from the choking grip of fossil fuels. But as the blades turn, so too does the dark underbelly of this green revolution reveal itself. Wind energy, once hailed as the savior of our planet, now finds itself caught in a maelstrom of controversy, its pristine image tarnished by unexpected environmental costs and logistical nightmares. Welcome to the turbulent world of wind power, where the road to sustainability is paved with good intentions and unforeseen consequences. Wind power has long been touted as a frontrunner in the quest for clean, renewable energy sources. The image of sleek turbines dotting landscapes and seascapes has become synonymous with progress towards a greener future. However, as we delve deeper into the realities of wind energy implementation, a more complex and challenging picture emerges. The promise of wind power, while not entirely hollow, has proven to be far more difficult to fulfill than initially anticipated. At the heart of wind energy's challenges lies its fundamental nature: the wind doesn't always blow. This simple fact creates a cascade of complications for energy grids and power supply reliability. Unlike traditional power sources such as coal, nuclear, or natural gas plants, which can provide a steady, controllable output, wind farms are at the mercy of atmospheric conditions. On calm days, wind turbines stand idle, silent sentinels producing no power. During gusty periods, they might generate more electricity than the grid can handle. This variability creates a significant challenge for grid operators who must maintain a delicate balance between supply and demand. The result is a need for constant backup power sources, often in the form of quick-start natural gas plants, which must be ready to fill the gap at a moment's notice. This need for redundancy undermines one of the primary arguments for wind energy: its environmental benefits. While wind turbines themselves produce no emissions during operation, the necessity of maintaining fossil fuel plants as backup negates a portion of these gains. It's a paradox that highlights the complexity of transitioning to renewable energy sources within our existing infrastructure. Even when the wind is blowing, wind turbines face another set of challenges rooted in their mechanical complexity. At the heart of each turbine lies a sophisticated gearbox, designed to convert the slow rotation of the blades into the high-speed rotation needed to generate electricity efficiently. These gearboxes, marvels of engineering in their own right, have become the Achilles heel of wind turbine technology. Designed to last for 2 decades or more, many gearboxes fail in less than a third of that time. The reasons for these premature failures are multifaceted, involving the interplay of extreme forces, variable speeds, and the harsh environments in which turbines often operate. The relentless torque exerted on the gears, combined with the start-stop nature of wind power generation, creates conditions that accelerate far beyond initial projections. The consequences of these failures extend beyond mere inconvenience. Replacing a gearbox is a major undertaking, often requiring large cranes and specialized equipment, especially for offshore wind farms. The costs are substantial, both in terms of the replacement parts and the lost generating capacity during downtime. For wind farm operators, these unexpected maintenance issues significantly impact the economic viability of their projects. Despite these challenges, wind power remains one of the most cost-effective and fastest-growing energy sources available. According to the National Renewable Energy Laboratory, wind farms have a relatively small permanent footprint, disturbing less than 1 acre per megawatt of power output capacity. This efficiency in land use is a significant advantage, especially when compared to other forms of energy generation. The potential of offshore wind is particularly promising. The International Energy Agency suggests that offshore wind farms could potentially generate more than the world's entire current electricity demand if fully utilized. However, this would require massive deployment of turbines along coastlines, raising questions about visual impact and marine ecosystem effects. While wind turbines are often celebrated for their clean operation, they do have environmental impacts that cannot be ignored. In the United States alone, it's estimated that as many as 500,000 birds are killed in wind turbine collisions each year. With wind energy capacity due to increase significantly, this figure could reach almost 1.5 million annually. However, it's worth noting that these numbers pale in comparison to bird deaths caused by other human activities and structures. Interestingly, offshore wind farms have shown unexpected benefits for marine life. Studies have found that the underwater platforms of turbines can support thriving ecosystems, acting as artificial reefs. A typical wind turbine can support about 4 metric tons of blue mussels, and the restricted areas around offshore wind farms often become de facto marine preserves, offering sanctuary to various sea life. Public perception of wind energy remains a complex issue. While many people support renewable energy in principle, there's often resistance to wind farm projects in local communities, a classic case of "not in my backyard" NIMBY syndrome. This has led to difficulties in siting new wind farms, particularly in densely populated countries. One of the most pressing challenges facing the wind energy sector is the issue of turbine disposal at the end of their operational life. While about 85% of a turbine's components can be recycled or reused, the massive blades pose a significant problem. Made from composite materials designed for strength and lightness, these blades are difficult to recycle and often end up in landfills. However, innovative solutions are emerging. Some companies are grinding up old blades to create materials for construction or manufacturing. Others are repurposing decommissioned blades for playgrounds, bus stops, and even bridges. In Europe, a consortium has developed a method to use old fiberglass blades in cement production, reducing CO2 emissions in the process. New technologies are also being developed to address some of wind energy's shortcomings. In Poland, for example, an urban tech startup has pioneered panels made up of vertical rows of small turbines, designed to be silent, quick to set up, and less harmful to wildlife. When considering the full life cycle analysis of different forms of energy generation, wind turbines are only surpassed by hydropower in terms of overall environmental impact. This fact, combined with ongoing innovations in materials, disposal methods, and turbine design, suggests that wind energy's future may be brighter than its current challenges suggest. As we stand at the crossroads of our energy future, wind power's tribulations serve as a cautionary tale. They remind us that no energy source is without its drawbacks, and that the transition to a sustainable energy system requires more than just good intentions and technological optimism. The story of wind energy is not one of outright failure, but rather of a promising technology grappling with the complexities of real-world implementation. The path forward will require continued innovation, adaptability, and a willingness to confront and overcome unforeseen challenges. As we navigate the complexities of our energy transition, the lessons learned from wind power's tribulations will be invaluable in charting a course towards a truly sustainable energy future. This future will likely include wind power, but as part of a more diverse, flexible, and integrated energy system that can meet our needs without compromising our environmental goals or community well-being.